Now let's discuss the relationship of pressure and depth and the Pascal law. In the way that fluid can be neglected, the pressure in a fluid is the same throughout its volume. We use that approximation in our discussion of bulk stress and strain, but often the fluid's weight is not negligible. Atmospheric pressure is less at high altitude than at sea level, which is why an airplane cabin has to be pressurized when flying at 35,000 feet. When you dive into deep water, your ears tell you that the pressure increases rapidly with increasing depth below the surface. So, to discuss pressure and its relationship with depth, we will use the PHET simulation. So this is our simulation of fluid pressure and flow. So we have here a different design or different type of container. So we just use the simple container. Okay, then we have here a pressure, measuring the pressure. Then let's open the valve. Let's fill our container with water. Cool. Okay, so our fluid density is water, which is 1,000 kilogram per cubic meter, and our gravity is Earth, which is 9.8 meter per second squared. Okay, so let's use this pressure gauge to measure the pressure. So you can see here at sea level, the atmospheric pressure is 101.325 kilopascal. So as we increases the height of the pressure, we can observe the decrease also in atmospheric pressure. So we know that the Earth atmosphere is composed of layer of gases. So when that layer of gases is being lessened by increasing the height of the pressure gauge, so there will be a decrease in pressure. So this time, we will go under the sea, under the water. Okay, so let's open our grid. Okay, so as we observe, as we go deeper in the water, from the water surface, we observe the increase in pressure. Okay, so again, in our discussion in bulk stress or simply pressure, we assume that we neglect the weight of the fluid or the water. But in real life, the water's weight is not negligible. And we can observe here why. Because as we go deeper from the surface, there is an increase in pressure. So at 1 meter, our pressure is roughly 110.9 kilopascal. At 2 meter, roughly 120.5 kilopascal. So let's try to measure, or rather, let's try to calculate using our calculator. Virtual calculator, here we go. Okay, so to get our absolute pressure, we simply add the atmospheric pressure plus the gauge pressure. But how can we know our gauge pressure? Okay, so in our case, our atmospheric pressure is 101.325 plus at 2 meter, roughly 2 meter, we have 1,000 kilogram per square meter times 9.8, which is which is the gravitational acceleration times the height of 2 meter, and is equal to 120,925 Pascal. So how did I get this formula? So let's go back to our presentation. So we use this formula to get the absolute pressure. So absolute pressure is equal to PO, where PO is the atmospheric pressure plus density times the gravitational acceleration times height is the calculation per gauge pressure. Or we can simplify this one because we know that density times the gravitational acceleration is equal to specific weight. So if we multiply the specific weight with the height or the depth of our body in the fluid, on fluid, so and adding it with the atmospheric pressure, then we can get the absolute pressure. Hey, going back to our simulation, let's use this type of container and let's fill this with water. Yeah, so we can observe here that at 2 meter, this is 2 meter, at 1 meter, we have 111,000 kilopascal at this location. So if we lipat, change the location here, roughly almost the same measured pressure. So at 2 meter, we have 121, and here 120 Pascal. Almost same. Let's try this one. So also the same, 120. Therefore, despite of its location or orientation, as long as it has the same depth, we're going to have the same um, measurement of pressure. So let's have our sample problem. The figure shows a cross-section of a swimming pool. Points A and B are both located at a distance of 5.5 meter below the surface of the water. Find the pressure at each of these 2 points. So we already know and discussed that at any location or at any orientation, as long as it has the same distance or depth from the surface of the water, it's going to have the same pressure. So in our given problem, we know now that point A and point B has the same pressure. So we're just going to get or calculate the pressure at any given point, at a given point or height of 5.5 meter. Yeah. Okay, so solving the problem, we use our formula P is equal to PO plus the specific weight times height. And we know that the specific weight is equal to density times the gravitational acceleration. Okay, then we're going to have 101,325 Pascal plus the density of water is 1,000 kilogram per cubic meter times the gravitational acceleration of 9.81 meter per second squared and the height of 5.5 meter. So summing up, therefore, roughly we have 1.55 times 10 raised to 5 Pascal. So this will be the pressure at point A and point B. Okay, so let's test your understanding by solving the next problem here.